Hello everyone, my name is Dr. G. Ranjith Kumar. I am working as an associate professor in Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. So today I am going to explain the next topic in power electronics from the module 1, which is the Scr gate characteristics and the commutation techniques. So first we will discuss what are the Thyristor gate characteristics. Then after that we will go for the commutation techniques of an Scr. So here these are the gate characteristics of an Scr. So here there are two curves that represents the curve 1 and curve 2. Here I have represented. So this is the curve 1, and here the curve 1 represents the lowest voltage that must be applied to turn on the Scr. The lowest voltage that must be turned on the Scr, and the curve 2 is the highest possible voltage value that can be safely applied to the gate circuit, so which is the curve 2. So which means you must give the gate voltage within the curve 1 and curve 2 only, because here the curve 1 represents the lowest voltage that must apply, which means the minimum voltage that must apply to turn on the thyristor, and curve 2 represents the maximum voltage or the maximum possible voltage that can be safely applied to the gate to turn on the thyristor. So which means we must apply the gate current within these two limits only. So as we know, to turn on the thyristor, we must apply the forward biased voltage across the anode and cathode, and as well as we must give the gate signal of a thyristor. So which means we must give a minimum gate current, okay, required to turn on the thyristor, as well as there is a maximum, or is that the gate current you must apply the gate current which must be below that maximum gate current. Then only you can safely operate the thyristor. So here, and again I am just mentioning a region like this. That line is called DE. Okay, so which means you must give the gate power below this region. So below this region, and if I draw a straight line from here to here and here to here, which means now this is the curve is CDEF. So which means you must give the voltage and the gate voltage and gate current below this operating region only. And as we know, there is a minimum gate current and the gate voltage that must apply to turn on the thyristor. So let me consider here, this is the minimum gate voltage and the minimum gate current that you must give to turn on the thyristor. So here the characteristics are in between Vg and Ig. Vg is the gate voltage and Ig is the gate current. So for our understanding, here I have shown a simple Scr triggering circuit. So here this is the Scr, and anode, cathode and gate is there, and for this gate we have connected one resistor, okay, to limit the gate current, and another one is here we have supplied some voltage, let us consider Es, and the voltage across this gate and cathode is the Vg, that is the gate current, and the current flowing through this gate terminal is the Ig. So we are drawing the characteristics in between Vg and Ig. So here if you indicate the point here, this is X. So here OX, the line OX, which represents the minimum gate voltage required to turn on the minimum gate current required to turn on the thyristor, and the curve OY is OX is the minimum gate current required to turn on the thyristor, and the OY is the minimum gate voltage required to turn on the thyristor. And the region here, let me take the region So if you consider the region from yes, so this region is the safe operating region of an SCR, or we can also call it as a gate drive area. This region is also called as the gate drive area. So which means if you want to operate safely the thyristor, or if you want to give the the safe voltage and current to trigger the thyristor, then you must give the voltage and current values within this region only, so that you can turn on the thyristor safely. And here, if you go through the circuit here, again the triggering circuit, then ES, which is the source voltage that we are applied across the gate and cathode, then this ES is equal to whatever the voltage across this resistor and the voltage across these two terminals, that the gate and the cathode terminal. So the voltage across this resistor is the current flowing through the resistor is IG, and the resistance of that particular resistor is RS. So IG into RS plus VG. And here the ES is the gate source voltage, and VG is the gate to cathode voltage, and IG is the gate current voltage, and RS is gate source resistance. So by using this equation, you can find the different variables like VG and IG. Next here, I have the characteristics. I'm going to explain some more details. Okay, so let draw again one curve. Okay, that is the curve 3, which is curve 3. In between the curve 1 and 2, let us draw the curve 3. So here actual the curve 3 is represents the VG and IG characteristics. The VG and IG characteristics, which means, so before drawing the curve, so let me indicate a point S. This S is the operating point. Okay, and if you just draw a line, okay, from through the point S. So let me draw a line through the point S. That line let me consider as a AD. So which means this is the load line, which is also called as the load line of the gate source voltage. The load line of the gate source voltage. So and the line which intersects the curve 1 is indicated as S1, and the line which intersects the curve 2 is marked as a S2. Then we must give the gate current and gate voltage to turn on the thyristor in between S1 and S2, the region in between S1 and S2. So which means how you can change the value from S1 to S2 to minimize the turn on time, because as we know, by increasing the gate current and gate voltage, okay, so we can change the turn on time. So to minimize the turn on time, we must operate the gate current and voltage in between the curve S1 and S2. And the slope of this AD line, which is the load line. So AD is equal to OA by OD. So here OA represents, of course here again there is a point which is called VGM, and there is here on x-axis also another point is IGM. Here VGM is the maximum gate voltage that we can apply to turn on the thyristor, and IGM is the maximum gate current that we can apply to turn on the thyristor. So which means we should not give the gate voltage which is above the VGM, and as well as we should not give the gate current which is above the IGM. So this is how the characteristics of the SCR. And here another point, from S, if you draw a straight line to the x-axis and again another straight line to the y-axis, Then here the line, the value OP, which represents the value OP, which represents the gate current. So if you want to minimize the turn on time, you must give the gate current, which is OP, so that you can turn on the thyristor as fast as possible. As fast as possible. So this is about the gate characteristics of an thyristor. So why we are discussing the gate characteristics of an thyristor means we must identify a safe region to turn on the thyristor. That is the first objective to discuss these SCR characteristics. And the second objective is we have to identify the required gate current and gate voltage to turn on or to minimize the turn on time of an SCR. So these are the two objectives behind this, the thyristor gate characteristics. Because from these gate characteristics, we have identified the gate driven region, which means the safe region. So in this safe region, you can give any current, gate current and gate voltage within this safe region, so that the thyristor will turn on properly. So without getting damaged, the thyristor will turn on. And second, the second what is that finding that we find is like the point, okay, because here the point which we have considered is S. Okay, so at a point S, okay, so what is the gate voltage and what is the gate current? Okay, so if you apply that much of gate voltage and that much of gate current to trigger the thyristor, then it will turn on as soon as possible. Right? So these are the two objectives of these gate characteristics. Then next we will go for the next topic, which is the commutation. The commutation of an SCR. So what is the commutation of an SCR? What do you mean by commutation? Actually, as we know, the SCR is a semi-controlled device. So which means we can only control the turn on, but we cannot control the turn off by using the gate signal. So which means by means of some extra circuit, we should turn off the thyristor, because the thyristor itself, it don't have the capability to turn off by itself. Then here the commutation is nothing but the process of turning off an SCR is called the commutation. The process of turning on is called as a is called as a commutation. Then if the thyristor, if we want to turn off the thyristor, then what are the conditions that we must satisfy? One is we must apply the reverse biased voltage across the thyristor, or a sufficient reverse biased voltage we must apply across the thyristor, okay, to regain its forward blocking state. Which means initially it is in the forward conduction mode. So if you want to turn off, first it will come to the forward blocking mode. Then after that it will turn off. That's why to regain its forward blocking mode, we must apply a sufficient reverse voltage. So if you want to apply a sufficient reverse voltage, then you must apply a reverse biased voltage across the anode and cathode. And then you must reduce the anode current below the holding current. Then only the thyristor will get into the turn off. So the thyristor must satisfy these two conditions, then only the thyristor will get into the turn off. One is you must apply the reverse voltage, the reverse biased voltage, and another one is you must take or reduce the anode current to below the holding current. Then only the thyristor will get into the turn off. Of course, there are different types of commutation techniques are there. Those are mainly there are two different types of commutation techniques, and these two different types of commutation techniques are differentiated based on the input supply. Okay, suppose if you are giving the input supply is AC to a particular thyristor, then in that case we use the natural commutation, or we can also call it as a line commutation. And the another type of the commutation is when we are having the DC supply, input as a DC supply, then in that case we use the forced commutation. And again, of course, the forced commutation can classify what is that again 4 types. One is class A commutation, we can also call it as a load commutation. The second one is class B commutation, which is also called as a resonant pulse commutation or the current commutation, and then class C commutation, which is also called as impulse or the complementary commutation, and class D is the voltage commutation. But unlike in forced commutation, in line commutation only one commutation technique is there, that is called the class F commutation. Then we will discuss one by one what is first we will discuss what is natural commutation, then after we will discuss forced commutation, the difference between natural and forced commutation. Then after we will discuss the different types of commutation techniques present in the forced commutation as well as the line commutation. So first one, the natural commutation. Here the name itself, it is indicating what kind of commutation it is. The natural, which means without doing anything. Okay, so by nature of the supply itself, okay, so it will turn off the thyristor. So that is called the natural commutation. So when the supply is AC, that time the natural commutation will happen, because as we know the AC supply, how it is like this. So it is having the positive cycle and the negative cycle. So if the input is AC supply, okay, then during the positive cycle, the forward biased voltage applied across the thyristor, okay, then when you give the gate signal, the thyristor will turn on, then you will get the output voltage. And after, when it reaches to 0, okay, then immediately the reverse biased applied across the thyristor T1. So in this case, here this is negative and this is positive. The anode is negative with respect to the cathode, so that the reverse biased voltage applied across the thyristor, then the thyristor will get into the turn off, so that there is no voltage. Again, it will get into the positive supply, the positive cycle, which means again the thyristor terminals has been changed to positive and negative. Then again the thyristor will get turned on. So this is natural process. So we are not connecting any extra circuit to turn off the thyristor. So because of the nature of the AC supply, okay, so automatically it is going to turn off when the negative, when the negative cycle supply applied across the thyristor. That's why this is called a natural commutation. So usually where we use the natural commutation, which means already we have discussed the different types of converters. Okay, so in the different types of converters, okay, so which converter having the input supply is AC, so all those kind of converters we can use the natural commutation. Then when coming to the what are the different types of converters which is having the input is AC, one is the AC voltage controller, and another one is cyclo converter, because which the AC voltage controller can convert fixed AC to variable AC, and the cyclo converter can convert fixed AC to variable frequency, fixed frequency to variable frequency, as well as the voltage. And when coming to the phase control rectifier, the fixed AC to variable DC. So in all these converters, the input is AC supply. So whenever there is a input supply is AC, then there we use the natural commutation. Then next, forced commutation. Forced commutation where we use means only in the when the input is DC supply, because as we know the DC supply like this always positive, so we don't have any negative supply. Okay, so the forced commutation used in a DC circuit, and it is also called as the DC commutation. The forced commutation is also called as the DC commutation. But here, to apply the commutation, which means to turn off the thyristor, we use the commutating elements like inductance and the capacitance. So in the commutation circuit, of course, we are going to develop a commutation circuit to turn off the particular thyristor. So in that commutation circuit, so the major components are the inductors and capacitors. So that's why these inductors and capacitors are called the commutating elements. So which means by using these commutating elements, we are forcefully reducing the anode current below the holding current. The anode current below the holding current. So that's why it is a forced commutation. Because it is not reducing the anode current below the holding current naturally. By forcefully, we are reducing the anode current of a thyristor below the holding current. So that's why this is called a forced commutation technique. And where we use the forced commutation techniques again, wherever there is a in any converter, if the input supply is DC, in all these converters we use then forced commutation, because as we know, the chopper, it will convert DC to DC, so input is DC. That's why here we use forced commutation. And in inverters, it converts DC to AC, so again input is DC, so here we use the forced commutation. Then we will discuss one by one the different types of commutation techniques. So the first one is the class A commutation. This is also called as a load commutation, because here, because of the nature of the load, okay, so it the thyristor will get into the turn off. That's why it is a load commutation. So because based on the load, so in the load we are using of course here R is the load, let me consider, but in addition to that R, here we are adding the L and C elements, the inductor and capacitor elements, in series with the R load. So that's why here the capacitor and inductor are used as a commutating elements. So these commutating elements L and C are connected in series with the load resistance if the value of the load resistance is low. So because here, based on the value of the load resistance, we will connect whether, these, especially the capacitor, whether it is in series with R or parallel with R. Then if the value of the load resistance is very high, then L is connected in series with the resistor, but C is connected in parallel with the resistor. Then when coming to the process, how the commutating elements will be used to turn off the thyristor. As we know, here this what is that RLC series circuit. Okay, so the nature of the RLC series circuit is underdamped in nature. So as we know how underdamped circuit will behave. Okay, so it is something like this. So after some time it will get into the steady state, right? So because of the nature of the underdamp, so initially the current will gradually, it is rising, okay, up to certain point, then it begin to fall to the zero. So when it is increasing up to O to A, then the capacitor will get fully charged, okay, and if you increase furthermore also, the capacitor will not allow to get charged, and then it tends to reverse, which means the current will get into the reverse. So which means at a particular point A, when the current will get into the reverse, then automatically the thyristor will get into the turn off. Which means here it is plus and minus up to O and A. Then after that, when it is fully get charged, then it will trying to discharge, so that the thyristor terminals will change, so that the reverse biased voltage applied across the thyristor, so that the thyristor will get into the turn off. So this is very simple commutation technique and very simple commutation circuit. This is about the class A commutation. Because of the RLC circuit is in underdamped nature, so because of that reason only the thyristor, the commutation process is happening, so that the thyristor will get into the turn off. Then the class B commutation. So this commutation is also called as the resonant current commutation, or simply called as a current commutation, because by using the current here we are going to turn off the thyristor. So this is a simple circuit of the class B commutation. Here we are using two thyristors, thyristor T1 and thyristor TA, and also one diode is there, and what is that, one inductor and the capacitor are there. Of course, here the inductor and capacitor and diode having a specific function or specific role to turn off the thyristor T1 and TA, right? Then how the thyristor T1 and TA will get turned off? So before that, here we should have some assumptions. The first assumption is the capacitor initially it is fully charged. That is the first assumption that we should take. And the second assumption is the load current is always constant. These two assumptions we are going to take to discuss the operation of the commutation B. Right. So first let me consider in the first case. Okay. So if you just apply some voltage, okay, if you simply the thyristor T1 and T2 are in the first case the thyristor T1 and TA are in the turn off position. Then you apply the voltage, okay, then the capacitor, I'm taking how initially the capacitor is fully charged. That's what I'm going to explain, right? So before the capacitor is there, but now we are going to full charge of this capacitor. So for that reason, so here the TA and T1 both are turned off. Then if you apply a voltage, then the load current will flow in this way. So that the capacitor will get full charged and up to Vc is equal to Vs. So once the capacitor get full charge, then the terminals of the capacitor will be takes place like this, plus and minus, like here. So once the terminal has been formed, then which means this anode is connected to the negative of this capacitor. So which means here the reverse bias gets applied across the diode, so that the diode will get into the turn off. So that is happen in case 2. When the terminals has been formed plus and minus, okay, then the capacitor, the diode has been turned off, then there is no path to discharge this capacitor. There is no path to discharge this capacitor, because here of the inductor it is an open circuit, and in this way here it is also turned off. Then after that, initially by giving the gate signal, we are turning on the thyristor T1. We are turning on the thyristor T1. So in this case, the load current will flow from this point to thyristor T1 to load 2 in this way. So in this case also, the capacitor don't have any path to discharge. And then in the next case, again we are going to turn on the thyristor T2, which means TA. By giving the gate signal, we just to turn it on thyristor TA. So now there is a path to discharge the capacitor, that is in this way. In this way, it will get discharged. So once it is fully discharged, then again the terminals of the capacitor has been changed. So once it is get full discharge, then the terminals of the capacitor has been changed. So that is again once it is fully get discharged, then again it will plus and minus. Then which means the reverse biased voltage applied across this thyristor TA, because here the anode is negative with respect to cathode, so that the thyristor TA will get into the turn off. That is, you can see in the case 5. Okay, so minus and plus. Then because before the diode was in the turn off position, so when this terminal has been changed as a minus and plus, then the diode will get into the start conducting mode. Then the capacitor again will flow in this way. Okay, which means again a reverse biased voltage applied across the thyristor T1. Then the thyristor T1 will get into the turn off. The thyristor T1 will get into the turn off. So here the main key element to turn off the thyristor TA and T1 is the capacitor, the charging and discharging process of the capacitor. So here we are turning off the thyristor T1 and thyristor TA. So that's why here the capacitor is a commutating element. Then why we are using the inductor here? That we will get to know when we are going to discuss about the protection of an SCR. Right? Then when coming to the waveforms, so these are the output waveforms for this class B commutation circuit. So as we discussed the process, initially we are turning on the thyristor T1. In the first case, we are turning on the thyristor T1. So when the thyristor T1 is turned on, then the load current will flow from T1 to load to this way. So that's why here, because here when you give the gate signal IG for the thyristor T1, then the load current will start flow like this. Okay, so that the IT1, the current is also, the current flowing through the thyristor is also same like the I0. But here during the thyristor T1, okay, so there was no discharging path for the capacitor C, so that's why the capacitor current still it is 0. Right, the capacitor current still it is 0. And whatever the capacitor voltage, because initially we have considered the capacitor is fully charged, so whatever the supply voltage that we are applied, it will come across the capacitor VC. So VC is equal to Vs. So that's why here the capacitor voltage is Vs when the thyristor T1 is turned on. Then after that, what we are doing, we are by giving the gate signal to the TA, then we are turning on the thyristor TA also. When the thyristor TA is turning on, then the capacitor will, we are providing the path to discharge the capacitor, so that the capacitor will get discharged. So which means the the voltage is gradually decreasing, and the current is also in a reverse way. So that's why you are getting the reverse current. And in this case also, because still the thyristor T1 is in the turning on position, so that's why we are getting the load current constant, and IT1 still it is in the turn on position only. So that's why here we are getting the current flowing through the thyristor T1 also. But when it is discharged fully, and again then the terminals the terminals has been changed as minus and plus. The terminals has been changed minus and plus. Okay, then the capacitor will charge in reverse direction. The capacitor will charge in a reverse direction. Okay, because here the supply Vs is there. Right. So when the capacitor is get charged, okay, then up to Vs. So once here, when the capacitor is charged fully in a reverse direction, so that the terminals has been changed. Okay, so like here minus and plus, then the thyristor TA will turn off. So at a time T2, the thyristor TA will be turned off. When the thyristor TA will be turned off, then because of the terminals has been changed, then the diode will get into the conduction. Then immediately there is a reverse biased voltage applied across the T1 also. Then the thyristor T1 will also turn off at an instant of time T3. Okay, so this is how the output waveforms for the class B commutation circuit. Then we will go for the class C commutation. This is also called as a impulse commutation and also called as a complementary commutation. Why we are calling this commutating technique as a complementary commutation? Because by giving the gate signal to the thyristor T1, we are going to turn off the thyristor T2, and similarly by giving the gate signal to the thyristor T2, we are going to turn off the thyristor T1. And how is here is the process. So let us consider initially the thyristor T1 and T2 are in the turn off position. Okay, then and the capacitor remains uncharged. Okay, so that here when in the next case, if you turn by giving the gate signal, the thyristor T1 is turned on, then the load current will flow in two ways. Okay, first is the capacitor current and then the load current. The load current will flow from this voltage source to RL2 thyristor T1 to the negative supply of the source, and then the capacitor current will flow from the positive supply of the source voltage to R to the capacitor to through the thyristor to the negative supply. So in this way, the capacitor will get fully charged, and the VC, whatever the voltage across the capacitor, VC is equal to the supply voltage that we have applied, Vs. Then in the next case, to turn off the thyristor T1, we are going to turn on the thyristor T2. Right? So here now by giving the gate signal, the thyristor T2 is turned on. So before you can see, how the terminals of the capacitor, here it is plus and minus, because capacitor was charging in this way, so that's why the terminals has been formed plus and minus. So, and in this case, once it is formed, so there is no discharge path for this capacitor. So that's why here we are to give the discharge path for this capacitor, we are going to turn on the thyristor T2. When the thyristor T2 is turned on, okay, when the thyristor T2 is turned on by giving the gate signal, then the voltage across the thyristor T1 get reverse biased because the capacitor polarities has been changed. Because the capacitor polarities has been changed. So that's why here the thyristor T1 gets turned off. The thyristor T1 gets turned off. Then the load current will flow here. The capacitor current. There are two different types of load currents here. Which is flowing here. One is through from here to here to here, and another one is from here to here. So the charging of the capacitor is done through the load resistance by path plus V2 minus RL. RL to C2. The capacitor negative terminal to SCR-T2 to Vs. But in this case, the capacitor charging, the charging of the capacitor is done in the reverse direction. Then again, if you want to turn off the thyristor T2, again you have to turn on the thyristor T1. If you turn on the thyristor T1, then again, here you can see the terminal has been changed. Then the reverse bias apply across the thyristor T2, so that the thyristor T2 will get turned off. And then again, the process will repeat like this. In this way, we are going to apply the commutation. So that's why it is the complementary commutation. Complementary commutation, because here, as you can see, by turning on the thyristor T2, we are going to turn off the thyristor T1. That's why here, once if you turn on the thyristor T2, then immediately the thyristor T1 will get into the turn off. And then if you want to turn off the thyristor T2, then you have to turn on the thyristor T1, then immediately the thyristor T2 will get into the turn off. Again here, the major role is the capacitor, which is the commutating element. So by charging and discharging process, we are turning on and we are turning off the thyristor. Then in the next class, we will discuss the class D and the class E commutation techniques. Then after that, we will discuss the class F commutation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.